Hello. Oh my god. Differential equations jump scare. Hey, how's it going? Oh wait. Sorry. Just want to make sure that the fun music ended. Oh god. Okay. Hi, how's it going? This is not... Oh man, I kind of just have like a lot of stuff that we could do. It's so exciting. There's like 3... Wait. There's like 4... No. There's like 3 things we could do. I mean, technically 4. Like at any given time, which is so exciting. It's not just like one thing anymore. Oh, I'm gonna turn down my music a little bit. But yeah, new quarter, new classes. I'm back, I'm here. This is series solutions to homogeneous ordinary, I want to say they're ordinary? Homogeneous linear differential equations. They're not necessarily ordinary, I don't think. I did this wrong. There are 2 things I did wrong. I didn't divide this, which I did wrong again when I redid this problem, and then the other thing I did wrong was, where was it? Wait, I might not have done that wrong here. I think there was one time I like changed this index and it was like not correct the way that I did it. But I think it's because I forgot to do this. I did this like after I... Silly. Anyway, we're not doing that. We're doing fluids. So let me get my fluids stuff. We love fluids. They're so fluid-y. I have a lot of things you can do for fluids. The other thing is, like, I don't know... I'm supposed to be reading a textbook. And guess what? I'm not doing. I'm reading a textbook. But he's using it a lot more than I thought he would, so I actually have to go and read that at some point. But that is not going to be now. Why am I so... Why does it look so small in here? I don't know why. I look like tiny to me. The differential equation wall. I don't know why that just hit me. Okay. Anyway, I think we could probably do this. We could probably do this. Maybe. Actually, okay, we already... Okay, I should probably... let me think about this. What would be a good one to do? Calculate fluid speed for each of the... Yeah, let's do this. Actually... Should we do the harder one? What do we think? I could do the harder one here. Let's do the easier one, just because it's the first problem. All the problems are very long. They're not long, actually, I lied. They're actually sort of short. I have to do them on... What are we doing here? Well, this is a series solution to a linear differential equation, but we're actually doing fluid mechanics. Oh. I forgot if I have to put my... Okay, we're gonna turn off the heading. We're gonna turn off the heading. I have to do my stuff on engineering paper. Whoops, don't look at that. But yeah, I'm an engineer. I'm a mechanical engineer in undergrad, and taking a fluid mechanics course, and so we do fun stuff here. Generally my VODs are kind of, or my streams are kind of all over the place because I'm learning the stuff. I'm not teaching it. Sometimes I'll teach it, but that's usually not when I'm taking a course. So yeah, we just hang out. We just chill out. We do some math. We do some physics stuff. We do some complicated math sometimes. It's usually not that hard math, honestly. Yeah. So for this one, let's see. So we have Pitot static tube, which is like a little tube that we use that uses differential pressure. Nice. I'm a high school student figuring out random shit. Oh, that's awesome. Are you interested in engineering or math or... 2 unique pressures measured independently, stagnation pressure and the static pressure, and then a differential between them, and we can figure out the dynamic pressure. I think this is a units question. Calculate fluid speed U in each case. So we can do that. But we have to make sure we do the units correctly. So let's say for case 1, like, writing is important in classes like these. Math largely been investigating tessarines much deeper than they have been before. Ooh, That's exciting. A lot of the math that I do is very applied. Even when I did, because I also did comp sci, even when I did comp sci stuff, it was like mostly for AI, so like linear algebra for AI, or you know, matrix manipulation, things like that. So I started learning real analysis at one point, but have not got back into that, sadly. I like it though. It's really cool. I want to do more theoretical math, but it's hard because I haven't, it's a lot of proofs. Writing proofs is hard when you haven't gotten instruction on how to read proofs. So we're in kilopascals. Let's just write everything out. I should probably write 2q divided by p equals, right down the bottom. Maybe testosterines will be applied eventually once people actually know how to use them and aren't being misled by shit papers. Wait, what are they? Is it a geometric? Tesserines, let's see. Biocomplex number. Complex numbers are... Oh. Split? I don't even know what split complex numbers are. You want to try? I mean, if you have a good definition, a good introductory definition. I always find it's a good way to test your knowledge by trying to explain things. Although I've heard in math, people are like, well, I can't explain anything because my field of study, you know, I can't, people don't know enough for me to be able to tell them. There's too many words. Yeah, give me a sec to explain. But as an engineer who deals with things that are also complicated, I never really have an issue, but maybe it's because it's applied. It's a little easier. Let's see. I'm just gonna go into regular units. So 1.32 times 1,000 pascals. We love our units here. So Pascal is force per area, so that would be pounds force. Nope, we're in newtons. Newtons per meters squared. And then kg per meters cubed. So we can cancel this and cancel that. Then we have the square root of 2 times 1.32 times 1,000 newtons, which is kilograms per second squared. What are we looking for? We're looking for velocity, so it should be, or fluid speed, meters per second. Did I goof a meters? Oh no, it's going to be on the bottom, so it'll go up top. Okay, take the complex numbers a plus bi. Add a new unit. Oh, my astigmatism, not my astigmatism. My bad eyes. A new unit j that satisfies j squared equals plus 1, and j not in the complex numbers. For convenience, I times j equals k. A plus, wait, okay, yeah, I didn't, j, a plus bi, j quantity, a plus b, equals aj plus bk. Okay, this creates a 4-dimensional number type, which is commutative. Further extensions can be achieved by adding more basis vectors to square, that's square to plus 1. Oh, that's interesting. Is that not, like, what's the point of it? Like, could you not just project things into a higher space or define things in, oh, I guess it's probably for definition of like real numbers in a 4-dimensional space or something without really changing the real numbers. Maybe I'm wrong. That maybe sounds sort of right. kg per, wait, kg meters per second. Wait, what the? Why do I not know my units, bro? I'm an engineer. I do this shit all the time. A unit. kg meters per second squared. Yeah, I don't know why. Okay. And then kg per meter. This, and then you get the square root of 2 times 1. This is not even really a question I should be doing. It is pretty simple. It is just units, but you know, it's good to practice writing stuff and being. Edward King Solomon knows a bit more than I do currently about how it can be applied, but it has a potential application to special relativity and connections to ellipses, plus connections to election fraud. That's another thing entirely. Wait, that's so cool. Honestly, also, I love math things that don't have applications, but I tend to like, because I mean, one of the interesting things about math is like, or I guess one of the things about engineering and math is it gives you like a real appreciation for different, you know, definitions of like spaces and how we describe spaces or points or whatever, because things can be so much more, you know, sorry, I'm trying to put something on my mic here. Things can be so much simpler if we try and define it in a certain way, you know. That's true for a lot of things. But that's why I'm always like, you know, I feel like there are some systems that are going to be like super useful in places that we like don't even know yet, you know. And that's always really cool to like be on that cutting edge of stuff, but I never get to do that. It also has non-values that are zero divisors. Wait, non-zero, wait, so like stuff that breaks the universe if you divide by it that's not zero? Wait, that sounds hard though. Wait, why would you want to do that? Let's make more spaces where our functions don't function. Where's my calculator? One sec. This is simple. We should do some actual fluid mechanics things. But I can take a look at what other units that we might use, because we're probably not going to be using English units. I'm in America. 1 plus j and 1 minus j are zero divisors. Oh, yes. That's fascinating. So you have j, wait, let me scroll up, because I'm getting mixed up with ijk and Ava. Okay, I see. That's fascinating. That's so cool. So is it a research type thing? I'm assuming so. 1.2. Wow, why did he just like give us something that was nice? He never do that. I guess I should probably check sig figs. Ew. Error propagation is what I probably should call it. Smarter. I don't know why I did that. Let's see. It's given in, I mean, rule of thumb, probably like just 2. 47, and that would be in meters per second. All units and show all of the conversion factors. Yep. PSI to pound. Ooh, slugs. Can you explain a bit more what you mean? I already forgot what I said. What did I say? Oh, research? Just like if it's something that's being utilized, like you want to learn it because it's already known sort of the things about it, versus like people are still learning things about it. Maybe that wasn't maybe that wasn't what I said that was confusing. Okay, let me get a better thing here. This is garbage. Get out of here. Do that one. That one's easy too. That one's also sort of easy. This one is a lot better. We could do the MATLAB one too, but we'll do this one first. There is existing literature that says the test ring conjugate basically doesn't exist. I figured out the natural log 40 of a 40 test ring was able to extend that to higher dimensions, and with that it gives you the conjugate in 5 days on my own. So I don't know what they were smoking. Maybe you're just built different. Maybe you're just built different. That sounds awesome. No, that's so real though, because sometimes I'm like, oh, I like get this, and it's like, why did other people not see that? But I think it's just because, I don't know. When you're still like in school, your brain is really flexy, and so it takes you longer as you get older to like flex that brain. The whole document thing that you're writing them? Wait, you're in a high school? That's crazy, dude. That's awesome. Okay, assuming velocity distribution, profile, whatever, shown in the diagram, which is a parabola having its vertex 4 inches from the boundary. Having its vertex... Oh, I see. It's this way. Okay. I have to remember what that equation is. My school helps me with none of this at all. Yeah, that's how I feel. Calculate the velocity gradients for the locations. Also calculate the shear stress. Let's do the... Wait, calculate the velocity gradients. Can I do that right now? I may not be able to do that. Notice how you're calculating number of quantities. Consider deriving equations. I don't know if I can do that. Maybe I can. So it would be... I mean, I can calculate... Wait. Okay, no, I maybe can. Can I? I have one equation. Well, so, okay, like, to preface, I started learning stuff from this class before my professor got it, so I know more. But the only thing he's actually given us is just this. Nope. Wait, which side is it? Let me remember. I think it's this way. What is it? TYX? I don't know, it depends on the plane. It's the only equation we have. So I don't... This is the deformation rate, but that's not the velocity. But it could be the velocity gradient is the thing, because gradient is like a, you know, hand waves. Gradient is like a distribution, right? Got to the point because some bozo online asked me a question. I damn near invented a 4-dimensional number system to answer the question they asked about why is it that if you conjugate everything's on both sides of the equation, that is negating all instances of I, the equation still holds true. But wouldn't that be like inherently true, hopefully, for for a coordinate system? Oh wait, no, if you conjugate everything. That is interesting. Because that wouldn't be the case for like... It wouldn't be the case for regular complex numbers, right? I mean, not necessarily, inherently. When you say conjugate, are you saying like x, let's say like is a plus bi? Are you saying like you're multiplying both sides by like, you know, whatever's over here, and then just times this? Or like its own conjugate? It's not true for the real numbers, yeah. I don't think I can do this one yet. Maybe I can do the MATLAB one. If not, I'll just do mate stuff. This one might be... yeah. This one maybe we can do. This is just a dynamics problem. I might have to find one equation extra for this one. But this one, I just don't have an equation for it. I mean, I guess I could just go on the equation sheet and find it, but like... I love lectures assigning homework that you can't do until like... Basically, they were asking for why it's not true for real numbers. Negating the real part on both sides does not guarantee it is still true. Oh, well that makes sense, right? Doesn't that make sense? Because like, aren't you like sort of changing the numbers? Like, in a very dumb way of putting it. Maybe I'm not understanding. Also, wait, so the BI counts as the real part? Or... in your complex part is the CD? Stuff? Both of the two? Okay. Yeah, I could do this one. Alright, so we have a copper block, and a smooth steel ramp. This is such a big problem it doesn't even fit on the slide. EI is imaginary part. Oh, not tesserines. Got it. We got an angle of incline, 30 degrees, put in there. And the length of the incline is of no importance in this problem. Between the base of the block and the incline is a thin film of SAE30 oil. Okay, that's important. Gonna have to look that up in a table for, you know, viscosity. Neglect gravity-driven flow by oil film. Okay. Neglect aerodynamic drag. Okay. Block release from rest, and given all the information in the problem statement, what does your intuition lead you to think about the velocity of the block? There's probably some, here, we'll do A over here. Probably some, okay, remember you're neglecting the aerodynamic drag force. So you'd have, you know, your block, and you would have gravity, just a simple little FBD, and then that would cause some, you know, acceleration on the block in that direction. And it would it be constant? I think what we're saying, we're neglecting gravity-driven flow, so we're gonna assume that, like, okay, we're not neglecting the fact that the oil needs time to, you know, start up as well, I guess. So I think this acceleration would change, but it would get to a point where it's steady. But at the beginning, it would change because their velocity is of the oil is also sort of getting to the point where it's, maybe is the block would be driving that, so its acceleration wouldn't be. There'd be some amount of force though. I don't know. I don't think it would be mostly. It would probably mostly look like a constant acceleration, I guess. So something like that. Let's see. I said it was probably because we defined I as square root of -1, or I squared -1. Wait, let me read in a bigger thing here. Those eyes are too small for my eyes. Let's see. Which is multi-valued plus or minus, as in plus I and minus I are both solutions, and that the same thing probably happens if you add a new unit that is specifically defined as square root of +1, or yeah, that makes sense. So that you can negate squared is probably sure. What do you think I did next? The next reasonable step? Oh, I don't know. I mean, you would have to prove it, right? Yeah? No? That's like v of, I mean, I guess I could say v of t, v of x. No, I lied. This is time. And this is v of time. Yes. The block is released, what's the initial acceleration? Yay, a basic dynamics problem. We don't have to do any work. Friction, you know what? I'm gonna pretend like friction. There's definitely friction from the, wait, but if it's just released at rest, what's the initial acceleration? Is there friction? I want to say there's like no friction because the velocity of the fluid. Wait, I gotta look this up. We haven't talked about this. Is there friction from a fluid? Wait, let me think about this. Fluids can't sustain a shear stress. So when a shear stress is applied to them, they're gonna deform. They're not like capable. I would say it's no. I don't think so. What? Wait. No, fluids exert friction. What? Oh no. Well, okay. Drag. But like not drag. I'm not talking about drag. Like if you have like a thing on water, if you have a, good question. Let me read. Let's see. Multiplication, division, exponentiation, trigonometry, square root, natural log. Oh, yeah, yeah. That's logical. That's like just doing other stuff. You're proving by example. Except for the one example that you haven't found that disproves. I'm kidding. I've never gotten to do any kind of that stuff. That stuff sounds cool though. I wish I was better at proofs. I drew this free body diagram already. I don't need to draw it again. One of the forces in X equals MAX. Okay, this is 30. This is 30. So we say mg, this is a block. I'll leave it as that for now. Mg, blah, 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 blah. It's x this way. Cosine, sine. Lol. Sine 30 equals max cross. What are we in? We are in kilograms, so it'll be 9.8. 30 equals ax equals... The exponential series and the main 4 trig function, main 4 trig series are the most useful things I've had thus far. Series, like... How are you defining them? Like with... Series is in like sums, or series is in like just a chunk of stuff? 9.8 sine 30, 4.9, oh that's nice. And that's in, I should put units on this number. 9.8 meters per second squared, and that's meters per second squared. Derive an expression in symbolic form for the speed of the block as a function of time. Comment on whether you think your expression makes sense. Okay, that's easy. We take an integral. Integral of ax dt, oops, of a dt equals b. Something like that. Oh, infinite series. Oh, that's cool. So just like power series versions of them, or... I mean... It's like what I'm doing in differential. It's funny because like what we're doing this class for... I mean, it's like Laplace transforms for a... that stuff, but all about like having a metal rod and having a temperature at one end, and then how that temperature propagates in various situations over to the other end. It's like a whole class just about that. The power Taylor series, that's cool. 4.9. This is not dt. Is it t? Am I? Oh yeah, that's t. What am I talking about? Jesus, man. V of t. I hope it's of t if we're in t. Okay. Comment on whether you think your expression makes sense. Consider manipulating each variable in the equation. Each variable. This probably means I need to have a friction in there. But I don't know what that force would be. I'll read a textbook. Fine, I'll read a textbook. Where's my... oh god, it's what are they called? I forgot what they were called. I could only find like a scan of this textbook that was like 3 pixels tall, I think. It was also named something different. Yeah. Something like this. Fox and McDonald. Yeah, that was what it was. 8th edition. I see. Oh, yeah, I'm coming back. I see. Okay. Use that to figure out things like e to the ix, e to the jx, e to the kx, and that earned me... Whoa, wait, that's so cool. Ew, that last thing is kind of gross. So you're just proving that those things hold true as well? Or just like having ways of that's like very... How did you get into doing math stuff? My high school would never have had me do that stuff. I need another force. I need another equation. It's loading. Yeah, only having one equation for like this rate of deformation. I stopped listening to myself. That's true. Yeah, I like to teach myself stuff. It's more fun that way, for sure. Better experience, I think. But you know, I will say there are good professors you'll meet if you know, go and meet professors, I guess, is the caveat there. Let me also grab my... I'll put that up. Supporting documents, sulfuric acid. Good supporting document, just called sulfuric acid. Problem 8, is that what we're doing? No, what we're doing? 10A. Hey, this looks like a dynamics problem. Visual rep changes at all the forces of play. The humanity needs to relate one of those. Yeah. I know, I can't do friction. They told me something was impossible 3 times too many and I proved them wrong. Oh, that's cool. Here we go. Fundamental concepts. Can I get some equations? Can I get some density equations? Okay, that's density, that's fine. Can I get some friction type equations? Some flow stuff, maybe? A bit of flow. A bit of flow for a poor lad. This is all stress. This is... Yeah, ty x equals u mu dy dx. But will that... Wait, okay. I think about this. It is a force times an area is a stress. Wait, maybe we can just use that. So this is a normal stress on... It'll have a normal stress on the fluid. The g sine... So g sine 30 is our like normal... A normal stress. Now, the area, I'm not sure about the area. Oh wait, it would be the area of this copper block. Okay, so we got an area. Get out of here. How do we know? I guess we know the deformation rate. We can say the stress that's created, so we know. Okay, okay, okay. So we say the stress on the y face of the fluid in the x direction. I'm not gonna worry about negatives. Is the viscosity of the fluid times the deformation rate of the fluid, which I think it's du dx. Or yeah, du dy, du dx, whatever. No, it's not whatever. It is du dy. It's an actually important distinction. Let me see. Talking about complex numbers. Exciting, interesting. Started looking at complex numbers and trying to understand why and how complex numbers exponentiate other complex numbers. Why that is cos x. I have to try to prove it. Took me 3 days and a couple pieces of paper with no internet reference. Oh, you're just built different, for real. My brother does that kind of stuff. He likes to prove things like that. I was always much more like, I wanna think about models physically. I don't want to have to make models, but I enjoy thinking about the relationships of things. Like proportionalities, I guess. Or like direct relationships or inversely proportional. Because I like to go, oh, if I make this thing bigger, this thing will be smaller. Yeah, du dy. I think there's got to be one other thing in here though, because we need something about how du dy. Okay, so we can define this at least. So this is wrong. Get up here. A free body diagram is not free. There's a force this way. Somehow. Well, I'll call it F. I don't know. Be an entire Desmos. Wait, did you say library? Whoa, what? Built different HF awesome. Hell yeah. Dude, I think neurodivergency is just like... That's how we get certain great things in the world. You know, find your niche and just like go all in. being a jack of all trades is no fun. I love people who zero in. Okay, this is G sign 30. I'm gonna leave it in, I'll just call it A for now. Well, I guess A is not gonna change. So I'll do 0.2 meters squared. I'll just square the whole thing. Okay, so we have this is a known. And this is a known, which means we can find this. It's like du dy is gonna equal G sine 30. I guess I could even do theta in there, but again, theta is not going to change, so they're asking us for, oh, they're not really asking us for a changing thing, that's fine. Divided by times 1 over the viscosity, which is going to change from this, if in the second example, the oil films. So we got that. Now there has to be something about this deformation and the proportional stuff. Okay, that is for non-Newtonian stuff? Question mark? Oh, I gotta read that later. Surface tension, okay, that's not super useful. This viscid and inviscid, or viscous and inviscid. Laminar, yeah. Okay, useful definition of streamlines. Oh, I should look at that. Lol. Shear stress for a non-Newtonian fluid. That is, I want a Newtonian fluid. Wait. Oh, that's fine. Is it a 1D flow? Yeah, it's a 1D flow. Don't need to worry about that. Don't need to worry about the dimensionality of flow. Where is this? Do I need fluid? I need fluid dynamics, but the next chapter is fluid statics. I don't understand. We need like something to determine, unless it's just like a one variable equation, but that seems way too easy. It's definitely not it. Okay, now we get into differential equations. Thank you. The gradient. Let's see. The pressure gradient is equal to the specific I don't care if it's equal to specific gravity. I don't need that. I don't need a pressure gradient, bro. Oh my gosh, you have a little link to it. That's so cool. Wait, let's see. I love it. Whoa! Oh my gosh. Wait. Wait, that is so cool. Wait, we're going on a field trip. Look at this. That's so beautiful. What the heck? Wait, that's so gorgeous. Oh, it's so beautiful. What's the red? Whoa! Oh my gosh, you can change it like with this? Yes, the first introduction of a new viewer to the mic demon. I am sorry for your ears. I don't know why that happens. I need to like uninstall my computer and reinstall it, and I haven't done that yet. I've tried. Awesome. I'm so sorry. The plus side is if you ever want to, I edit all my VODs so that they don't have ear-splitting mic noises. So if you don't want to, whoa. What? What does it do? I like just messing around with things. This is great. This is like, oh. Whoa, I can play it. Okay, I probably shouldn't do that. Where's the C equals min value? Wait, oh, is that? Wait, what moves? Oh, it goes back and forth. Whoa. Whoa, can I play one of the other ones? Oh, wait, what if I change this? R? What's that slider called? Oh, covered by chat? Sorry, my bad. That doesn't fix it. Here, let me move chat. It's C min value. C minimum value. Sorry, this is funny. Whoa, what are all these colors? Oh, these are just colors. Wait, if I change it, can I change it? What if I change it to 220? What if I change it to 3? What if I change it to 100? Oh, it changes. See, menu value is supposed to be a very small function used for function debugging. Oh, sorry. Sorry, like an epsilon. Let me reload it. I don't want to leave page. I don't want to mess up your epsilons. Usage documentation. How to write complex number. Wait, so C angle. Wait, so like what can you do with it? Whoa. Oh, I see. So you can like use these functions to draw stuff? It's fine. Yeah, that's so cool. Oh my god. What's this? What's this? Oh, you can't see it. It says R set equals 501 element. Oh, it says it. List of exponent reciprocals starting at 0 and zeroing out after 177. Oh, so you just like can import these functions to like something that you wanted to do and then you can draw it. That's where you change. I see. Whoa, that's really cool. How do you, what even is this? That's crazy. I can't believe you made this. This is like awesome. This is like actually really, really cool. Wait, I can play it and it goes around in a circle. Wow, it's like my baby sensory. I love math. Dude, people who can do this stuff are like wizards to me. This is like spell casting. This is literally just check the docs for the full function list. Oh yeah, I've been opening the full function list. I just haven't. You can't. The chat is in the way. Get out of there. I like how you put in colors as well. That's awesome. This section is unfinished. The shape reminds me of a Mobius transform. Oh, the README folder? Where is that? Oh, here. The real unit. Okay, so it's real and that's a match. Oh, look, you even labeled the axes. Oh my god. You're cracked. Okay, to access the real part P, use P dot X, imaginary part P dot Y. E circle, return complex point. This is such a cool visualization. How did you make the like the swirly like graph this thing? Like I never label my axes. Oh, I always label my axes because okay. In engineering, people like to label their axes whatever the hell. I don't like how Minecraft uses messed up axes. And so I just never assume, so I always label mine. Tetrate infinite. What? These are so cool. E to the complex C. Wait, does it also like graphic? If you just say like, I don't know how to write this. Wait, give me something cool to write. That's the last folder. Takes the red grid and plugs everything into it through a complex function. Oh, I see. P grid A. Oh, let me move. Units are a waste of paper? No, literally, you can't. You can't. In engineering, they crucify you if you don't write all your units. Change this to modify the density of the grid. Whoa, I can make it big as hell. That's awesome. This is so cool. Everybody go look at the link. It was in chat. From me putting chat in the, just replace everything after the equal sign in the PA grid. PA grid. Replace it with what? Oh, to graph something cool? Oh, I see. I don't know what I would put. Like, can I put like sine x? No, no, I can't. No, I can't. I don't know. Like with f cosine f underscore. Oh, oh, f underscore like that? No. Have to replace everything. I see. We can't have a cool rectangle. Wait, when you say underscore, do you mean like sub? Really? Like that? Cos. Oh, f cos. Yeah. Okay. Okay. Wow. Wait, that's so sick. I don't even know what that like is. That's so. It's like. Whoa! It looks different. No way. I'm like literally baby sensory right now. Oh wait, so like cosine probably was on the other side too. Oh, oh no, it was only on one side. Wait, why is it only on one side? Why only one? Why are you so one side? Why are you so one side? What if we say E? Or you could say like E, right? E. No. What was it? There was an E. Resize red grid. Oh wait. Oh wait. Oh, red grid is like a bounding box. Whoa! Wow! Whoa! That's so sick. How do you? Whoa! What is that? What does it going down like that mean? Where is it? Because that means that it's like in the imaginary space, right? And any real bit is along the real bit. That's wacky. That is so sick, though. Holy shit. What? So if it was only like 2, we put it only here. It doesn't make cosine. Could you make like just like a regular cosine function? I guess if you did like this. Wait, where's 1? The box is not like exactly the box. Wait, that's so weird. What are the limits of the box based on? Doesn't seem like I mean, I guess maybe that's not pi though. That's also not pi. E is exponential. I made a Mobius transform graphing script, got a 2D one working, tried to graph it onto a Riemann sphere too, but had trouble with FP. That's, you guys are like, I'm over here like, okay, let me do my stress analysis, FEA, I'm gonna put it into SolidWorks. You guys are built different. I don't know what to say. That's awesome. Oh, I put the chat right over the I was just doing like this. I was going, woo. And the red grid lines as a set of complex points and plugging them into the function. That's really neat. That's awesome. It's like a mouth. That's complex cosine. Oh. Wait, is it kind of looks like it's like almost like an optical illusion of like a column. Do you see that? That's kind of swag. Complex input, complex output. One of the graphs before was f square root of a. F square root. Whoa! Ooh, that one's pretty. I like that one. Ooh, that's cool. I like it when it's like that. That's like awesome. Right there, right on the line. Took a complex analysis course last semester. We didn't get to these kind of graphs. Finished up on Mobius transforms and VVP. I hate to break it to you guys. Unfortunately, I'm an engineer and I do boring stuff. I just stream in the math category, and I'm a bit of a fraud for streaming in the math category all the time. But I do stream. I do stream in the math category. I don't know. I'm also studying engineering. Oh wait, but you say you don't use units, huh? What kind of engineering? Here, wait, we can take math for electives. I wish I could do that. Oh my god. I might try and take a minor, but it is rough, man. Wait, let me open this in a different browser real quick so that we can go on an adventure together through the land of fluid dynamics. Oh, I was joking. I might take a math minor though. I love math. So this work helped me do tesserines. That's so cool. Tesserine is like a beautiful word. It's like, that's an awesome word. Wait, this is a different... What? It has different headings? A what? A what? Chapter 3, Fluid Statics. Wait, I'm not in chapter... Oh, oops. I'm in chapter 1. Wait, I need to go chapter 3. Why are they all open? Basic equations. Can I just go to, like, the end equations so that we can see if they give me anything that I can work with? Okay, pressure variation... No, I'm not looking at any of that. I need like, I need something about like the resistance. I need the resistance. Fluid mechanics is lame. I love fluid mechanics. Fluid mechanics is the best. Do you do labs? No, we don't have labs for fluids. It's just chunking fluid mechanics in your MP3 player. Everybody wants to know. Okay, maybe let's see. Is there any dynamics problem they do? Like, they literally am just missing the way that we connect the dynamics to the thing. RE. Oh, the Reynolds number equals VL over. Wait, no, that's Wait, in chapter 7, what? Characteristic and flow, well, viscous effects. Okay, that's not. Oh wait, no, that is maybe, but it's like a shear. That's the only thing. It's not like submerged in water. What's the line count on my graph at the bottom? Oh, they canceled our labs too. Calculations without context. Oh no, this is like very contextual. Line count? I think it's 900, right? No, 491. That's how many. It's actually very contextual. My professor is pretty good. He just like, this is due, actually it's due in 5 days, so hopefully he would have taught us some of this stuff. But I think there's just one little bit that I'm missing. So like, this is, okay, let's see. The shear stress on the upper plate. Wait. My brain, it's thinking. I think maybe I did it backwards is the thing. Professor loves switching calculus notation styles in the same line of working. Oh my god, I'm so sorry for you. Wait, like, how would you even do that? Like double prime to just like d squared dx squared? That would suck. I think I flipped this. Do I have a deformation rate is the thing. Because I want to say... Okay, wait, let's see. Oh, wait. Big brain. Wait, are we trying to compute T? No. Ooh, giant brain moment. Okay. It's not this. This is not... It's not a shear. It's the normal... That would be F over A, but our shear is gonna be... Wait, do I need to do VQIT for this? I hope I don't. I do not know what either of those are yet. Oh, okay, your complex graphing looks very similar to a Mobius transformation. My first fluid mechanics class. Yeah. I'm a sophomore. It's my 3rd quarter as a sophomore. I'm getting there. I always get a little self-conscious when I stream because usually it's either people who know nothing, which is great for me, or people who know everything, and then I'm just like, I don't know what inviscid flow is. Although I do know what inviscid flow is, okay? That one I know. What am I looking for? I need to see, oh, I need to see that. Yep, this is that. I just don't know, because we talked about shear, but like we didn't. They're teaching you better than us, goes further than the fluids class I did? Did you have to do Fourier transforms and linear algebra? So the prereq for this is our class called linear analysis, which, linear analysis 1, which is basically just linear algebra and homogeneous first order, second order differential equations. So we do differential equations. We don't do Fourier transforms, but we have a fluid mechanics 2 class, which does have a prereq of our linear analysis 2, which is what I'm taking also now. And that's Fourier transforms, and oh, they actually teaching you probably. My school is so shit. Well, it's interesting. So they teach us, I go to an engineering accredited school, and so they teach us a lot of the very specific stuff, but they don't really teach us as much design stuff. So the analysis stuff is pretty good, but the design stuff is pretty bad. Complex analysis. Oh yeah, complex analysis. That's exciting. That's like, complex analysis is like grad school stuff, I will say. Yours is accredited too, but also shit. Oh no. I would hate to go to a shit accredited school, because I want to do design. I like analysis, but it's boring to me when there's no design. Does complex analysis include the tessarines thing? Probably, right? Because I mean, like, the other kinds of analysis, I know you can like be an algebraist, or like you can be a geometry, or you can work with like topology, or you can work with like set theory or group theory, and it doesn't sound like any of those. What am I doing? What was I looking for? Oh yeah, a definition of shear stress. Oh, they say it's G theta. Okay. I don't know if I would say it was that. Would I say it was that? G? I don't. What's G? What is G? I know G is like for torsion, but we're not talking about bars. We're talking about fluids. I don't know. I'm going a little insane. It's okay. Tessarines fall under purview, probably a subfield. They're kind of like quaternions. Oh, quaternions. Got excited. Sorry. Okay, we can back stuff out here. We can back stuff out. Because yes. Okay. Wait, I'm cooking. Give me a second. Okay. First off, this is gonna be. I'll call this force XY. It should probably be negative. Well, it is negative. Don't worry about it. Okay. So the shear stress XY equals force XY over area. So that means that Fxy equals the shear times the area. I think they're quite different from quaternions. They're more an extension of complex numbers than quaternions are. Yeah, that's true. They are both sort of fourth dimensional things, which might be why they seem similar to... Oh god, there needs to be a theta on that. Okay, let's leave it in theta for now. I don't want to deal with that. We can find the G of SAE oil. Where's my 44-page packet of with all of my fluid properties in it? Sorry, that was Velcro. Wait, I could just look this up and it would be easier than me looking at my packet. SAE oil 30 G. There we go. Okay, well, it's not giving me the G. G property, fluid mechanics. What is it? What does G mean? Oh, specific weight. Okay, that's the density divided by the density of water? No, it's the density times gravity. You're not spinors. Whoa. Similarities end at them being both fourth dimensional. Yeah, they got 4 numbers though. They can be described by matrices. They don't need to be. Does who know? I don't know about spinors. Matrices are the best. I know about tensors. I like a good tensor. G effective. Yeah. Whoa. That's not it. It's the specific weight. Okay, specific weight is density times... Not density, density times stuff. Density times gravity. So this is, I'm gonna just leave it in this stuff. So density times gravity times theta. Which means that F this equals rho g theta A. Alright, now, so theta is going to be the deformation of, the angle of deformation of the fluid element. So that's going to take a time to get up to a steady state. So it'll go, you know, it'll slowly go, but there will be a theta that we end at. I even describe single numbers as matrices. Yeah, that's true. This means seemingly it might be easier to work with and derive stuff for in non-matrix form. I don't touch linear algebra with complex variables until next semester. We did some. Wait, no, we definitely did some, because we did eigenspaces. We did phase spaces and eigenvalues that are complex. And both of those require... Whoops, I turned off my music. Both of those require complex numbers in linear algebra. They're not that hard. I'm surprised you didn't just like throw them in there, because they're really not that different. Not sure I would have been able to derive natural log by looking at matrix form. I sent the Google Doc I'm writing. Oh wait, yeah, I saw the link and I didn't open it because I forgot. Let me see, test rings. Whoa, how many pages is this? Wait, it actually looks awesome. Oh, I thought it said latex. Oh, it does. It does say latex. I started learning latex. I can't tell how many pages it is. Oh, my mouse just died. That's fun. It says it's on green. I don't know why it died. You should put an outline in it. That would be nice. Wait, let me put on my music real quick before I look at this. I'll scroll over on the thing as well, so that everyone can see the beautiful work, because it's actually pretty beautiful. Look at this. Look at how nice this is. You're all zoom in. Okay, I turned the text size up. That's not what I wanted to do. Wait, why can I edit this? Don't let me edit it. Okay. This is so cool. A new kind of product table. Have you had anyone else look at this yet? Or is it still like work in progress type beat? Might do complex eigenvalues, but that's not like spinors or tesserines. Oh no, no, nowhere near. They're useful though. Haven't yet, because I was working off a school Chromebook. Oh my god. Oh yeah, well, that's true. Dude, you're like... Oh, 76 pages. That's crazy. That's so cool. No, wait, this is actually awesome. I do need to find the density of SAE oil 30 real quick. Wait, no, I don't. I don't really care. I can just leave it in terms of... Wow, this is awesome. I'm gonna read through this for sure. Oh, over the summer, I might try and learn a little bit of real analysis or... Oh, Cayley table? Whoa! Oh shit, that's so cool. I might try and learn some analysis stuff, so. I probably would never be as good as this. I'm like, whoa, look at the colors, they're so nice. Collab with Edward Solomon, whoa. Do you know them, or is this just like a collab because like you're working on stuff? What did I need? Density. Density. Spell it correctly. Dynamic viscosity density in grams per cubic centimeter at 30 degrees. What temperature were we at? some temp. At 20 degrees, the one they don't give me. I don't know if this is a good site. It says that it's 0.8787. Let's think. Water is like 1.2. Right? Water's like 1.2 or 1 point something. Oil's less dense than water. Good. We're winning. It's probably somewhat right. Random person I found on Twitch who is investigating tesserines. Wait, that's so crazy. Sorry, I'm slurping up all the math stuff. I'm really not supposed to be in the math category, but Twitch wouldn't care. Okay, so we've got gravity in the positive direction, so that's mg. What do we got? Cosine, lol. Nope, it's sine. I swear I'm an engineer. Minus that rho g theta a. Now theta is kind of sticky. I don't really want to deal with that. Oh, well we can also, so density is, so let me do this. G sine 30 minus rho g this a divided by m. So density equals mass over volume. And then if we divide by mass, we're gonna get 1 over volume. So that's kind of nice. Our mass doesn't matter. Math category means I might show up at some point. Ooh. That's, oh wait, I thought you meant you were gonna stream. There's some cool, it's hard because like, man, every time I find a cool math person, they always like stop streaming. Actually, wait, there's one person, I'm trying to remember their username, and Stucky. Wait, I can do a shout out, can't I? They do, a bunch of different, oh, I just didn't do that. Shout out and Stucky. Not a shout out, but that's their name. They do math, like straight up math stuff, and like go through papers, and they're pretty active. They're also sometimes in my chat. I'm less in theirs because I'm different time zone, but let's see, what else can I get rid of? Well, maybe we can define theta as something as well. Theta would be a, I might stream at some point. I haven't in like 2 years. Oh, hey, if you ever do, drop me a link. I will be there if I can. If I don't have class or something else. I want to say we can get this even better. I think there's something about the theta that we can define with horse stuff. How would we do that? I'm thinking. Let's see. Well, theta is like, it's like the difference between the velocities at the top and the bottom. That's what would define the theta. Somehow. So maybe we just go straight up geometry type beat on this. This is V1. I guess it's more apt to say this is V1. And this is V2. I don't really know the velocities, so V2 minus V1 will get us this distance. And we, our height, because we could say like, you know, cosine or something if we knew the height of, oh wait, we do sort of know the height. We do know the height. How much I've been talking about tesserines. I wonder how many people would come in asking questions about them. I also came up with a challenge problem related to the zero divisors. Oh, drop it. I don't know how many people are in the know about tesserines. Let's see, so this is theta. We want to say, what do we want to do? We could do, I don't have any tangent, right? We don't want really anything else in there. So tangent is this one, height. So h over right? V2 minus, or delta V. Yeah, I'm gonna say V2 minus V1. Okay, let's see how well I copy-paste multi-line message into single-line Twitch chat. I don't know. It should be okay. Oh. Oh, it's bigger than 500 characters. Yeah, for sure. If you want to, you could put it in the Discord if you wanted to, or you could just send me like an image of it, or you could put it somewhere else. The Discord for anyone who is, for anyone who is interested. It's mostly, I use it mostly for stream pings if you're interested in that. What was I doing? My entire brain turned off. I was trying to get an angle. I don't like the V1, V2, because I can't say, wait. Isn't that the deformation? Right? Is that not the deformation rate? We haven't used the deformation rate yet. Oh shit! Wait, because this is the change in, this is the deformation rate! So it's related to T! It's related to TX! Oh, this is du dy. Wow. Sorry, I got really excited about that. This is a good problem. This is a really good problem. Makes you think. Okay, then we have du dy equals mu t. I don't know about, let me check that, because he wrote it, I think he wrote it as mu on the same side as t, but then in the book it seemed like they were writing it the other way. I sent it in general. Let me take a look see. Yeah, he wrote it. No, okay, I'm writing it wrong. I wrote it on the wrong side. That would be the opposite way if we define things. There we go. As your viscosity goes up, your shear is, as your viscosity goes up, you get, what? Wait, that doesn't make sense. I'll figure it out. Let me take a look in general. Fancies. Given any starting real number s and any real difference d, if you construct a proper tessarine with binary vector index ordering, regular ordering, with the coefficients s plus d, s plus 2d, s plus 4d, s plus 5d, s plus 2n minus 1d, s plus 2n minus 1. Okay, sure. Is there a reason why you're not saying n? Why is it 2n minus 1? Am I just dumb? Maybe I'm silly. For any finite 2... Oh, I see. Because you're setting it up later. For 2n greater than 8, where n is an integer, it will always be a 0 divisor. 2n greater than 8. N greater than 8. I can see maybe how you might set it up. Tessarine dimensions are 2n dimensional. Ah, I see. So how many dimensions can a tessarine have? I thought it was only 4D. How do you have so many coefficients? Or can you project it into higher dimensions? And you're... Maybe I'm misinterpreting from my limited knowledge of... I got so excited about this. So as you have more shear, your deformation rate will go up. And then as you have more viscosity, your deformation rate should go down, right? But your deformation rate shouldn't go down. It should go up. Maybe I'm are larger viscosities more resistant to change? Higher viscosity, yes. Greater resistance. Wait, what did I write on this? I feel like I wrote this down and then I figured it out and then I didn't say it. Add more reflectors, vectors that square to +1, and multiply them by everything you already have. Oh, okay, that might be much more complicated than what I was thinking. That's crazy. I wrote higher shear, higher deformation rate. Yes, that makes sense. And then I wrote, as mu increases, du dy. I didn't write anything. Du dy. Mu is the slope. Oh, so if it was the same shear, it would be actually less du dy. But the slope would be higher. Because the slope is... Wait a second, let me draw this. This is important, actually. Let me check in this as well. I think they prove it a little farther down. Here, wait, we can take a trip over to Funland. That's the viscosity of engine oil. Okay, that's not what I needed. Well, that's a fun table. Everybody's favorite table. Where am I? I'm around somewhere. That's where they're proving... Oh, this is them proving. We can see where dA is an element in contact. Oh, they were like doing the thing that I did. Deformation rate equals the limit of... Okay, these are... I jumped in the middle of a proof. Wait, no, wait, I did write it on the wrong side. Didn't I? T equals mu... No, I didn't. I'm tripping. SAE 30W is harder to stir than one of water. It's much more viscous. Wait, okay. Did I look at the wrong... That's 15W! What? It didn't give me 30? Are you kidding me? I searched 30. Oh, you little stinker. Wait, SAE 30W. I'm probably looking at the wrong oil then. So like add m squared plus 1. Whoa, that's so many letters. WM plus XM plus YO plus ZP? What? N equals IM, O equals JM, P equals KM. Oh, I see. He does not see. Wait. So you have your regular tesserine, and then which is up to the DK, Donkey Kong. Donkey Kong is here. Sorry. WM. What is W? XN plus YO. I don't know what the W is. That's the only thing I don't know. That's the first Kale table I have in the doc. Oh, that's crazy. Okay, wait, sorry, my brain is like... You know? What am I trying to find? I'm trying to find an expression for theta. I'm realizing now that there's an easier expression for theta I could use. Theta is also this over G. Now if I say that, I don't know if I can say that is the thing. Also, if it's Fy over, I don't know if I can say this is the thing. I don't think this is true. If it's force over area, that's a normal stress. It's not a shear stress. Wait, did I write that and I just like didn't erase it after? Oh, I didn't erase it after. That's what happened. I was like, I can't. Why am I using that? This is correct. And then you set that equal because this is equal to. Wait, no, that was. I don't think I can do that. Or can I? I know that the shear in the block is the same, or the shear at the bottom of the block is the same as the shear in the liquid, but that's not really super helpful. Let's say I squared equals -1, I squared equals +1, and k squared is +1. Let's see. Yeah, I squared is -1, j squared is +1, k squared is +1. 8D with the factored out vectors. Oh, okay, you just picked W to get a fourth one. I see. I was like, what? Where's W going from? Wait, so why do you have, like, k squared as +1 as well? Why wouldn't it be, like, I mean... I can see redefined. But... Wait, oh yeah. Oh yeah, it's IJ, okay. I want to say, maybe it is this. Maybe it is. I can't see any other way of us getting a force, the actual force to the area. Unless I use VQ over IT, which you would say then the force is V, and then you could get Q from... I don't know, where did we get a shear flow from? I guess we just get it from the bottom of the copper block, and we use I from the bottom of the copper block and the thickness from the bottom of the copper block. I guess for this one, for sake of, I mean, this would work as an approximation if there is a different definition of it. But getting that theta, I don't know if I don't want to keep theta in there. There's too many variables, and theta can definitely be expressed in terms of other stuff. So we have tan theta equals h over du dy, which also equals h over, if we solve using this one, that would be the shear over the viscosity. So that would be h viscosity over that, so theta would equal tan inverse of that. And in this case, this would equal, I guess, f over a. We do know f, and we do know a. So this is a fully defined value. But that doesn't really make sense either, does it? There has to be some change in time. Oh, no, it doesn't. Is this for the steady state? What we're saying is du dy u equals t. That's for the steady state, I think. I don't think that's for the non-steady. Ooh. Ew. Also, there are connections to binary logic in the tesseraries. Tesseraries. That's theta for the theta for the steady state. Is that like an issue? There's a small, I mean, it's oil. I don't know. I mean, it's not gonna happen. It's gonna have a non-zero time to get up to that. But like, is it worth trying to say like, here's the function of time that this angle changes as? Like, I don't know if I have something to do that. I have the relationship with y, but I don't have a time. I think that's about as good as I can get. This is a single value for theta. To be fair, the theta over the g is also, that should be the same value. I don't know if they'd be the same value if I did them out. This is also all assuming that this is true, which I don't think is true. Alright, well, let's maybe just do it. So this is a constant. What's our non-constant? This is a constant, this is a constant. It's all constants. Wait, it's all a constant. Bruh. Because if I had theta as a function of, if it was theta of t equals blah, 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 then we would, you know, have a t in there to differentiate with. But we don't have a t, because how will we define theta as a function of time? You would have to figure out the acceleration of the fluid, and then say the difference in velocities as a function of time. But the difference in velocities... Wow, that's kind of scuffed, isn't it? You would have to, like, define the velocities as functions of t of themselves. Is this in a steady field? Would it be steady? Is uniform thickness at all locations? Would it be steady? I feel like once it hits a state, it would be steady. But it's gonna get accelerated by the block, and I mean, it's gonna also like move. It's gonna flow down the surface. Steady means that it's not changing with time, though, so it wouldn't be steady. We could define the velocities as a function of time somehow in some later chapter, I'm guessing. Fascinating. Anyway, this is my best guess. To be G sine 30. So it's only, you know, slightly different. I'm kidding. It's probably pretty different than the answer I had before. Times t equals vt. Comment on whether you think your expression makes sense. To consider manipulating each variable one at a time, check the resulting behavior. Okay, that actually is something I can do now. So as the density goes up, we're gonna get a larger number, which means... okay, a more dense fluid. It's gonna be... density related to viscosity? No. Not really. The reason we're using density is because we have a shear. That's our theta. As our density goes up... oh, here we go. As our density goes up, our theta is gonna get smaller. Which should mean our velocity... oh, wait. Our velocity at t... oh, I didn't put in my h. That would give us a position of the height. Sure. Maybe they just mean at the top of the fluid is the thing. Maybe I'm just like super overcomplicating this. But this does give us it as a function of h, which is kind of fun. Equals v of t and h. So as we go up... okay, I don't know what tan inverse though does. Let's see. Oh god. I missed messages. Let me read. With that construction above, just add another vector that squares to +1, and all the combinations in which each vector appears 0 or 1 times are different directions. So you have 4, 5, 4. I'm misreading. Oh my god, and then all the like combinations. Pretty easy pattern once you see it. Oh no, me when I don't see it. To be fair, I haven't done any proof stuff. I'm pretty poor at proofs. I can read a proof and I can understand what's going on if I read it like 10 times. And I, you know, have the appropriate background knowledge, but I'm pretty bad at general math proofs. Ignore the ANs. It's hard for me to read on the screen. Okay, here we go. So I, J, K, I, K, J, K, I, J, K, M, I, M. Oh. But how do you prove that that's like, if you have the 8, the 2 to the n is larger than 8? How does that prove that there's 0 divisors? Because I times j, so nothing. I, j, I. Okay, so you combine them all. I see. Let's see, if gravity goes up, I feel like it's so hard to manipulate this. I feel like I made this harder than it should be. But also, it definitely needs to have density and stuff in there. Maybe theta is just like, we don't do theta. If the area of the block goes up, the shear force, okay, if the area of the block goes up, the shear force goes down, the velocity should be less. That one makes sense. If the mass of, oh, and that's where we have a first error. That's the mass of the block, not the mass of this. So get out of here. If the mass of the block goes up, it's going to exert a larger shear force, which makes sense. So wait a second. That doesn't make any sense. The mass of the block goes up. It should have a higher velocity. I guess it has a higher acceleration, but not a higher... Oh, this is rough. I don't know if this is easy enough to... Because, like, okay, I put a bigger number in tan inverse. What do I get? I think the bigger number, which would make sense. As you go up higher, your No, but if you go up higher, your velocity shouldn't be lower. Oh no. Oh no. That on its own doesn't solve the problem, but it's a start for getting the right order. A solution involved manipulating the shit out of natural log function. Oh god, that seems involved. Okay, well that's my best guess of that. I don't think it's super right. Would the shear be going that way? What if the shear was going the other way, though, is the thing? I feel like maybe it's supposed to go the other way. Would the oil be like helping it or stopping it from moving? Well, no. The block is shearing. The block is definitely pushing on it this way. So it pushes on the block the other way. Well, we're talking about, yeah, the block. Speed of the block. Oh, wait, it's the speed of the block. Wait, why was I doing all this then? The speed of the block does not depend on the height of the fluid. It should only be... This is also just, that's not a variable either. Got it. Yeah, so this, as the block goes up, as the mass of the block increases, we have more force. And so our speed gets faster, okay? As the density of the fluid increases, it gets easier to move. Yeah, maybe. It gets, okay, it doesn't get easier to move, it gets faster to move. It might take more force, but it's faster to move. Which means that the velocity would go up. If gravity's increased... If gravity's increased, shouldn't it increase the speed? Well, okay, it's hard to tell, because this will be increased too. So this might account for this. And if there's more fluid, it would be easier to move? That seems a little weird. Also, if the density of the fluid is increased, it's more like if the viscosity is increased, it gets easier to move. If the shear stress of the block decreases, then hopefully it gets easier to move. Because there's less force there, even though this is kind of goofy way of saying that. It's kind of recursive. But it's also not because this shear is created by the block. Okay, that's decent. I'm gonna go with that. I'm not gonna go any farther though on it, because I feel like it's not super useful if I don't know how to do it. Most of the kinds of things follow that sort of logic. That one I should do, but later. That one, oh wait, maybe I could actually do this one. Like velocity gradients. Oh yeah, velocity gradients. We do that. We do know that. I just have to figure out, oh, I mean, that's fine. Yeah. Ooh. Don't render that. Wait, latex. Oh no. Okay, wait. Zero divisors are where you encounter natural log of 0 in the natural log function. Okay. Okay, I'll take that. Big thing, latex. There we go, fixed. Recursive natural log with a general tesserine. The first latex was broken. I don't know if I have a thing that can generate latex. Let me see. Go on an adventure. Let's go on a field trip. Latex generator. Math. I feel like it's important to put math on there. It says invalid equation. I don't know why. Let me try a different one. Oh, there we go. I don't know what the dollar signs are. The dollar signs aren't. Yeah, maybe remove the dollar signs. Yeah, the dollar signs aren't rendering. Or they're just rendering as dollar signs. Let me try that in the first one. Yeah, okay. Well, let's we'll field trip it up. Here we go. Q equals A plus BJ. X equals ln n minus 1 A minus B. E equals ln n minus 1 A plus B. Ln A plus B J is 0.5 X plus P plus J X minus P. Whoa, how did you prove that? Well, so X minus P would be like natural logs, like divided by each other, right? Which I guess you could prove. You'd get like A squared plus B squared on the bottom, and then wait, no, I lied. You would get A squared plus B squared on top. And wait, what am I talking about? How would you do anything with that? I guess you could do A squared plus B squared on the bottom, and then oh cool, because A and B are just numbers. I'll explain it in the document. Oh, it was a whole chain? Oh god. Okay. I'm getting spoilers for the end. Okay. We're trying to find the velocity gradient, which is our we'll say, so we say du dy velocity gradient is the viscosity, the times the viscosity is equal to the shear at any given point. So it looks like we're gonna just make a field. So we need u of y equals, okay, sideways parabola equation. Y equals x squared. That's how we do it. So y x squared. I want to go in Desmos and mess around. Cause that'd be fun. I got called brilliant for it, so that's nice. Holy shit, yeah, that's great. Getting called brilliant is like... That is not a... X equals y squared, what the hell? So that would be... like y equals plus or minus square root of x. Yeah. Yeah. Okay, so first we need to flip it the other way. There's a start. We need to translate it over a certain amount. We want the vertex to be at 4. That's gonna move it the wrong direction. And we want it to be up a certain amount too. So we have to figure out, okay, well it's giving the intercept, so that's kind of nice. I think I can just get the intercept in here. There we go. Simple as that. Is that right? I mean, it doesn't look like the parabola they gave, but it's like, it is right. I also have a C# program on .NET Fiddle implementing arbitrary dimensional test rings. That's so cool. That's so cool. Man, that's awesome. Oh wait, I need to say u of y. Also, whoops, let me, that's the couch. I need u as a function of y, though. So let's write this out. So we have x minus 4 equals minus y minus 2 squared. That's our velocity. So I guess we just need it in terms of like what? So x at any given point is our oh, my brain is thinking. So y is our input and x is our velocity. But is that like what we have? It's not what we have, I don't think. So essentially when we like put in here, we want to go over here. And what we have right now, so if I say like x equals 4, I have to say like y equals 4 to get 0. If I want to say like y equals 2, we get 4. So y equals 2, we get 4. So right now it is, so x equals u. So I have the code to prove that this shit works. Anyone who wants to challenge it has to explain why I get consistent right result in the code. I'll write what the natural log form was derived from. Oh yeah, go for it. So velocity, u of y equals 4 minus y minus 2 squared. That's what our velocity is. In symbolic variable form first. Oh yeah. I'm not gonna call it delta, I'm just gonna call it y. Y equals y. Like when we redefine, when we re-index things just to n again. Okay, well, so then the gradient of y is just, we take the derivative with respect to it, so I think it's just that. Yeah? Not 4? Don't know why I put the 4 there. That one's not there. That doesn't keep being there when we... It's been a while, okay? Negative 2y plus 4. So for y equals 1, or 0, we have 4. That's incorrect. That is not correct. Oh, wait. No, it is correct because it's a slope. What am I talking about? I was like, it's not the velocity there. When y equals 0, we should get 0. -2 squared, 4 minus, yes, okay, we do get that for the velocity. But we have a slope. Y equals 1, we get 2. Y equals 2, we get 0. Oh, that's 4 inches. Whoops. Sorry, not y minus 2, we want y minus 4. And then x. Oh, whoops, we gotta move it out. 8? Okay, I wrote 48, that's not right. Oh, 16? Yeah. Lol, squared. Okay. Okay, slightly different numbers. Don't know why I goofed that. 16. Well, I do know why I goofed that, I just didn't write it right. Usually how it happens. I saw 4, I went, that's the radius, not the... I saw 4, I said that's the diameter, not the radius. Slightly more gross numbers, but that's okay. 64. There we go. 0 is 64. 2 is 32. Nope. What is that? 64 minus 16, 48. 2 is 32. Y equals 3 is 16. And then y equals 4 is 0. Nice. Makes sense. Calculate the shear stress. Okay. Whoa, CP. C pascals? What is C? CP. Fluid mechanics unit, please. The center poise? A poise? What? A poise? A poise? Pressure coefficient. Oh, it's a dimensionless... Wait, but... The viscosity is... Oh, I see. It's probably like a specific viscosity or something? So it would just be 400 times... I don't know what our stress would be in... Yeah, du. So this would be negative 16y. Wait, did it solve for... Yeah, velocity gradients. Okay, return. Alright, I'm losing my brain a little bit. And then times this, which is 400 something. But I don't know. Fine, oh, let me see what your latex equation over here is. I think the solution to your problem is a 256 dimensional tesseract. Can that please be the new meme? Can we please just say every answer is a 200? I just copied the same thing. I didn't copy your thing. Whoops. I'm down. I think it is. I think it's also that. You could probably say it in that, right? Okay, this is what it is. So Q equals A plus BJ. I'm down with that. I like that part of the equation. I don't know about the rest of it. Z equals... Okay, A times hyperbolic tan of B over A ln in ln of n, I guess? Hyperbolic arctan, yeah. Oh, not A times... Oh, arctan. Oh, so tan inverse, yeah, okay. Whoa, that's even worse, sorry. So the ln at n of A plus B J is it's a recursion relationship. A over hyperbolic cosine of Z plus J. I don't know how you did that though. How did you do that? You just went, okay, yeah, this, then this. It's crazy. I don't know how that works. I mean, I like trust you, but like also like how? Derived from the exponential function. Oh, okay, okay. Pressure coefficient. Oh wait, I was gonna look this up in the actual textbook. Equations unuseful. Specific gravity. Can we get a basic equation? No. Oh, dimensions in units. Systems of units. The MLFT. FLFT. Wait, no, I want CP. I don't know what it is. Are given in Appendix G. They hate me. They hate me. They don't want me to understand what the unit is. Can I please get a unit? Can I please get a unit? Where's Appendix G? Okay. Oh, I think I was given this table. Where? What is CP? They don't even say it. Maybe it's poise. One poise, boys. It says pressure coefficient is the first thing that comes up. But that's weird. Oh no. I said unit, not that. How do we say it? Oh, it didn't say it. Poise. Okay, poise. The unit of the centipoise. Okay. So 0.01 P. P is 0.1 meters inverse kg per meter second. It's a dynamic viscosity. Okay. So kg per meter second. Kg per meter second, but this is a centipoise, so 400 times 0.1, I think. 0.01, so it's 4 kg meters per second. Maybe. I forgot what we were solving for. Oh yeah, that's good enough. It's fine. I don't really care about the numbers as much as I care about the units, so we're fine. Let me see what you're saying. Basically creating a ratio between left and right to plug into the hyperbolic cosine and hyperbolic sine. And then using recursive natural log to readjust back where it needs to be. Anyway, so I went back to the hyperbolic arctangent version to the first one I showed you through manipulating the equation. Okay, well, it's just manipulation. Probably just like my brain is not trained to recognize that kind of manipulation. Which is so often the case. They're equal. Kind of fucking crazy. Yeah, you know, sometimes it's just wild what stuff is equal. I could try and do this one. You said choose one of the two options to work on, but what if I worked on two? Okay, well, like, I'll probably do mate later tonight, so let's do this one. This one looks like exciting, you know? It looks exciting. There's probably some dynamics in here that the fluid dynamics is after. Look how long it is, and look at the cool picture. Okay, let's go. One instrument to measure the viscosity of a liquid is a rotating cylinder viscometer, illustrated in this figure. In this device, the outer cylinder is fixed and the inner cylinder is rotated with an omega. The torque required to rotate the inner cylinder is measured, and the viscosity is calculated from these two measurements. Okay, that's exactly what we're doing. Develop a model relating the viscosity, the speed, the torque, L, how long the area of contact between the fluids and the solid, the inner radius and the outer radius. Neglect end effects, i.e. do not consider the effects of the interfaces or the submerged bottom end of the cylinder. You might note that the bottom of the cylinder is curved to eliminate the end effect. Can you explain why that shape would be beneficial to reducing the effect of the viscometer cylinder end? Why that shape would be beneficial? Beats me. No, I'm kidding. And it does beat me, but why that shape? Probably because cylinders aren't going to exert as much, like they're not going to exert a shear in one direction. It's going to spread out the force in a bunch of different directions, and so it creates a lot smaller shears than you would have if you just had a big fat plane in there. Maybe? But maybe I'm incorrect. Okay, we have to figure out a model. That's great. Well, maybe we start with something we know. Probably Newton. Okay, so we know that the velocity gradient times the viscosity is the torque. So maybe let's figure out some torque. This would be, we don't really have, I would say y, x. Actually, it's not going to be that. It's going to be, it would be xy in this case. Normal, and then the direction of the shear. Actually, no, it's not going to be xy, it's going to be xz. What am I talking about? Because it's shearing it this way, or this way. So if this is x, this is x, that's y. Right-hand coordinate system. What? I think it might be going backwards. Dude. Is that right? I feel like that's not right. What's up? What's up, gamers? Yeah, cause it's not right. I put my fingers in the wrong direction. It does go out. Me when I'm goofy. Okay. So yeah, the shear would be in the z direction. Kind of fun. Okay. Well, what do we know about stuff? Trying to define a shear is probably the best option we have, because we can figure out some torques that we apply. So if we apply a torque to turn something, it's gonna turn an omega. It's constant speed, so we don't have to worry about acceleration. Well, one thing we know that torque is proportional to omega, so the more torque we put in, ideally the higher, the omega. And torque is like gonna be, proportional to 1 over viscosity. Oh, but we know that. Well, I guess not necessarily. That's the shear. This is, really should call that a different thing. This is going to be torque with a big T. What else do we know? Well, the more length you have, the more spread out your force is going to be. So length would be anti-proportional to shear. The more length you have. I'm just collecting stuff at this point. Right, and the length has to do with the area. So how do we find the area that's in contact? A equals, that's gonna be R inner Well, it's gonna be, what would that be? R inner, no, pi, 2 pi r inner times length. That's the area. But again, this is sort of the same thing in the last one where it's like I'm saying like force per area, but that's not really, I don't know if we can say that for shear. It's because that's for normal stresses. Although, I mean, to be fair, we'd still need to find the area if we were doing a VQIT thing. I don't know. Let me see here. I don't think he really talked about how to define the shear other than with the, I guess we could also figure out, so we know that each of the points that's in contact with the rotating cylinder is going to have the same velocity as it, and the same angular velocity as it actually as well. So we do know, we know these conditions. This one's going to be, so this is u. Ooh, we should also probably use cylindrical coordinates, huh? Maybe I don't say that. Maybe I say this. Maybe we say r and theta. Yeah? How do we think about that? I feel like that's a better... I wonder what weird ways I can define number systems with. How do you even define a number system? How do you start that? This will be theta. We're using cylindrical coordinates, not spherical. I guess omega equals Ri times, what is it? It's like omega equals VR, right? Times V. And our V, it doesn't really matter. Or wait, what are we trying to find? We're just trying to relate them? I guess. What do I do if, like, the absolute value... Oh, I see. So you just set some conditions up, and you just try and figure out something that does that stuff? That's cool. See, so A plus... The absolute value of A plus BJ equals A... The absolute value of A minus the absolute value of B. The absolute value of BJ equals... minus the absolute value of B? Wait, that sounds so confusing. How would you do that? I'm trying to think. What would we possibly use RO for? Ah, okay, well, you know what we can do? The difference between RO and RI is going to be where we get our... So our if we draw a little piece here, it's going to look like this. I should probably make a control... maybe I do that. I don't know what it's called. Control volume. So this is the cylinder. He actually draws nicely. He does something like that, which I think is quite elegant. For most professors tend to not really draw too nicely. I quite like it. Sort of like that. I don't know, it's not super nice. Pretty much the idea with that is, what if we were able to do negative absolute values? Wait, so are you redefining what an absolute value is then? Or is that just like a pipe? Not an absolute value, really? Anyway, this is the control volume here. So like this is DL. And then we have, I guess it wouldn't really be DL, but it's fine. That's 0 there. And this is omega over R. Omega over R I, I guess? No, it's not like that. I lied. Fuck. This is not like that. It wouldn't be like, wait, I gotta delete all this because I gotta delete that and I don't want to. I drew so many dots. Okay, there we go. It's like rotating around. This is 0. And this is moving this fast. It's like that. Ugh. So I guess it would be like, this is our control volume. We'll do something like that. Just imagine. Just take a journey with me. Something equals -1 for real x. I don't know, it's part of the process of figuring out. Oh, I also did figure out absolute value on test screens. Whoa, that's crazy. Wait, did no one else do that stuff before? This is omega R. That makes sense. Should I say here? I feel like I should maybe say there. I feel like I made this curve way too big. I'm gonna make it like kind of like that. I'll do here. Yeah, let's do that. Okay, that like kind of makes sense, low-key. There we go. This is omega over R, inner, and this is 0. This is U of R? No. Yeah, it's a function of R. As you go farther out, it changes. Nope, besides Edward Solomon, no. Everybody else fucking sucked. That's so funny. That's so funny. So du dr equals like the difference in u over, you know, the difference in r. So that would be this over r outer minus r inner. And then we can say, okay, we got one part. We want to propagate this duder. Viscosity equals something, probably r theta. I don't know, something like that. For tesserines, I'm looking. I gotta look closer. This is like an eye exam up in here. Okay, the absolute value equals square root of the absolute values of the conjugate. Huh. And reflector. So what is a reflector? Is that just the name of the component, like what you call that component of it? Okay, we got a viscosity. We have an omega. Omega's in there. Torque is not in here yet. Torque is not in here yet, and L is not in here yet. And I feel like we have to say, I think we have to say this. I think we have to say torque, this, whatever, R theta equals force over area. I don't see any other way we could do that other than Q, VQ over IT. And I mean, if we want to say VQ over IT, everything sucks. Everything sucks, man. I don't want to do VQ, because then I have to do the moment of inertia of the cylinder. Ooh, who wants to do a moment of inertia of a cylinder? Gross. Gross. This is a good enough approximation for right now. It's easy enough for me to switch. I understand what it is. Is this the torque, is the question. I didn't draw a free body diagram. Oh no, what am I even doing? I'm just floundering around in numbers. We don't even have a free body diagram to show for it. Hello? What kind of an engineer am I? Silly one. The one is. I'm a silly guy. Okay. Here's our free body. Don't worry. I don't know why the top is so defined. There's an MG. Very long MG. There's a torque applied this way, which has a moment, I guess. Sorry, that was a deep sigh. Which is a force that's pulling this way. I don't care about that. We're just gonna do a force pulling this way. I'm gonna make it as fat as I can. I could have drawn a better. You know what? Maybe I should just draw the free bond diagram from the top, since that would be smart. Okay. Well, we've got a moment here. This is our moment T, or I guess I could just call it T. And then our fluid is going to be trying to be pulled this way, so it's going to have this sort of adverse, sort of like fluid, like shear that's happening. And the weight we don't care about. Now, okay. This is definitely not F over A. This is like MC over I, which is a bar property. It's a shear applied to a circle. But you know what? MC, let me think. MC over I is gonna have L in it. You know what? Because, I mean, like, you would have to say, like, well, the shear in this is this, and the shear in this is a different value. And the shear in this equals the shear in this. I don't want to do all that. I'm just gonna say F over A. I'm the worst. I'm just gonna say it's T. I'm gonna say it's T, baby. Input T over R1 times L. And you know what? You know what? You know what we got us? W over Ri times the difference between these two times the viscosity equals input T over Ri times L. It's good enough, baby. It's good enough. It's an approximation. It's not. But I'm gonna put a note. Probably MC over I. Lol. Good enough. Definitely not good enough for government work, but for a problem that I didn't actually technically need to do, because he said only do one of them, and I did two of them. Of those two. Okay. Let me take a look. Let me see. Let me see what this reflector thing is. Sorry. Had to do some work. Okay, J. So J squared is positive 1 is a reflector. J squared is negative 1 is a rotator. So when you're saying that, is that like different definitions of a tesserine? When you're defining a tesserine, do you choose what your four things are representing every single time? So you really have... I'm buffering. It turns out to be the same thing technically. Wait, how does it do that? Because wouldn't you then have, like, reflectors are more correct? So, wait, so is it like I squared equals -1, J squared equals +1, K squared equals -1, L squared equals +1? Or more of them +1? I love how I'm just like stumbling through. You add one unit at a time, and the rest come as products of the units you added. Okay. So you say I and J are like what they are, and then you multiply I and J to get K. And then you multiply all three to get the next one? I can remember that. That's good. That's good definition. What was I doing? Let's see. Is there anything else? Oh, there's nothing else. I mean, there are easy ones. I have to look at different types of line definitions. I haven't done that yet. There's a question I want to do on that. I should probably also use an SDS for a data sheet, safety data sheets for stuff. Fomblin, trademarked oil. Wait, let's see. Wait, I'm running over to the comments. I see you in my peripheral. Well, IK equals negative J, JK equals plus I. Wait, my brain buffering. No, that makes sense. But you have 4, right? So is it like, because K equals IJ, yeah. IK equals IIJ, okay, yeah. So, but you have 4, right? So what's the 4th one? Is it IJK? And then when you multiply them together, you're gonna get, well, I mean, it's like a right-handed coordinate system, right? Or is it not right-handed? It's a coordinate system. Okay, I think I'm gonna do a little mate before we head out. It shouldn't be too hard. I think it's just about like packing. That's 207. Why did I open 207? Lol. Because I opened mechanics of materials. 4th is new vector, which is where you added M. So it was only for that one, or does it always have an extra dude? M, IM, JM, IJM. Oh, so when you have vectors, so it's like you have I, J, K, and let's say you have M. And so then you have K equals IJ. So like I and J are your 2 that are like distinct. And then M equals IJK. And then where's the vector part? Are the vectors like, are they like linear? M is not IJK? Oh, what is M? M is just a new thing? Oh, M is, whoa. Wait, but, okay, so how can you do that? Why do we say K is IJ and then M is just its own thing? I mean, okay, maybe I guess I kind of get that, because like in 3D space, if you want to go into 4D space and say like time, right, you would have like, you would have I, let's say this is I, J, K, and K is based off of these 2, but like your time is just like going off over here and doing its own thing, you know, it's like whatever. I maybe if it's like that, like I get that kind of. That's how you get to 8D. To go from 4D to 8D, you add a new direction. Oh, so that's just for the one setup of the problem? Wait, I'm confused on how many directions tessarines have. I thought they had 4 components always, or is that not true? I'm also gonna grab my, here we go. Homework 1. Okay. Some of these are easy. Let me make a new folder. There we go. Homework 1. Made it kind of big. 2 n components. Oh, so you can have like 2 or 4 or 8 or, but like why? Why not other ones? Is that just how it's defined? Okay, the force of attraction between a divalent cation and a divalent anion is, let me pull up equation sheets also real quick. Would it practice test? I don't know why he has that already. Final review. No, let me just pull up to the final review. No, I'm not doing that. Where's the equation sheet? Do we not have one? Maybe we don't have one. Maybe not. Link to Callister, Zoom class. Well, it forces itself to 2n via multiplication when you add new stuff. Oh god, I forgot the slides were like 50 slides. Hey, can I get some equations, my good fellow, my good man? Let me see. Bonding energy. Yeah, here we go. Wait, it's just KQ. I mean, it's been a long time since I did this. It's K Q1 Q2 over A squared. Right? Wait, ZQ? Wait, the attraction... Oh, this might be more involved than I want to do right now. I might just end soon. Yeah, I'm probably going to write stuff out for this too. Maybe I'll just take a break. I mean, it's not a hard question, but I don't really want to do it right now. Let me just check. It's asking about... force of attraction. Yeah, that would be FC. But I don't know. Divalent. Let's see what's going on now. Oh. Okay. It's asking. Okay, so it is Z Q times. Oh, Z times a fundamental Q. Yeah, it's okay. I forgot we're not in physics 3. Lol. We have to do chemistry instead. Like if we had AB, A plus BI, and we added C, I times J is not reducible to real I or J, so it's a different direction. Oh, sorry, CJ. Oh, I see. Oh, wait, that makes so much sense. Yeah, that makes sense. So it's like K is IJ. That's the direction of it. So when you have 2, you have 4? Wait. Yeah? You can have 2 as in like A, B, I. Like A and B. Or when you add another one, you have to have a thing that like is representing like the multiples. I see. So when you add M, it gives you like all of the different things. Oh, I get it. I get it. That makes a lot of sense. Thank you, that was a good explanation. And with that explanation, I think I'm going to head out for the day. I definitely plan on streaming this weekend, if I can. I'd like to. I don't know how busy my tomorrow is, but... because it'd be cool to do more fluids. I don't actually even know, because it's really weird. My fluids... some of these are really grindy, so maybe we'll just do a grindy day. Not as much, like, interesting, thinky stuff. Like, what is the stress on a... oh wait, I can do, like, a flyby. Well, it's also weird, because he's not going to collect all the problems. He might collect, like, 1, but he doesn't tell us which one he's going to collect until, like, after it's due, and then he's like, oh, well, we have like a certain... it's weird. But yeah, it's not too bad. It's, you know, it's 13 pages, but it's like a problem per page, so it's not too bad. I mean, there's some with 2 problems per page. But yeah, I'm gonna head out. Thank you guys so much for hanging out. It was really great to hear about your tesserines. That's so cool. If you ever want to come back and talk about tesserines, I would love to learn more about them, because I feel like I mildly understand what's going on now with them. But, You know, maybe I don't, but I try. And that was fun. You're very smart, and that's cool. I'm over here doing my silly little guy things. Yeah, I will be back this weekend, or if not, well, like, you can just check my stream pings, or I don't have a schedule really that I follow because my schedule's kind of all over the place. But I might be able to set one up later in the quarter. But yeah. I'll be back later. Have a lovely day, have a lovely night, eat some good food, get some good rest. Thanks for hanging out. Alright. Bye everybody. Bye. Bye.